So hi and welcome back. Today we're going to start moving away from the sources and things like that and get into the details of comparing petrodiesel versus biodiesel. Okay, so this is one of our fossil fuel biofuel comparisons that we need to know in detail in regards to their chemical reactivity, their physical properties, sourcing and environmental impact. So let's get started. So petrodiesel, as we mentioned, sometimes referred to as petroleum gas, those kinds of things. Petrodiesel specifically is part of crude oil that can be separated from fractional distillation. Okay, it is not, however, a pure substance. The fraction that comes off in the column, remember with fractional distillation, we're talking about heating the column and the fractions being different sizes as they come up. The fraction that comes off contains multiple compounds, okay? Usually it's around 75% C10 to C15, and it contains some aromatic compounds. When we talk about aromatic compounds, we're not talking about them having a strong aroma or being smelly. They are containing benzene rings. Okay, they contain an aromatic ring. So something like benzene, which this one is here. So when we see this in another group, we refer to this as a phenyl group. And we can see here benzene, substituted benzene with a CH3, which is toluene, xylenes, naphthalene, and these kinds of things. You do not need to be able to name these, but you do need to know that there are other aromatic compounds within the fraction from which we obtain petrodiesel. Biodiesel, however, is not obtained from crude oil. It is a fatty acid ester. Okay, so this is a carboxylic acid derived from a fat turned into an ester. Typically a methyl ester. Sometimes it can be an ethyl ester. Okay, but it's a small alcohol that is added to the large fatty acid in order to create biodiesel. Okay, so the long chains can be saturated carbon-carbon bonds or unsaturated carbon-carbon bonds. And you'll notice when we talk about the saturated or unsaturated, we specify that we are talking about the carbon-carbon bond within the chain. Okay, and that's critical. When you're talking about these, if you just say the carbon bonds or things like that, or the bonds, you're going to be marked incorrect. You do want to specify when you're talking about it that all carbon-carbon bonds are single, and then if we're talking unsaturated, that there is at least one carbon double bonded to another carbon. So this is formed by the reaction of a triglyceride, okay, which you remember from the other video is our glycerol backbone with our long hydrophobic tails attached, and they are what we get from all fats and oils have this structure. Okay, so all fats and oils have this structure, and we'll look at it a bit more in detail in the next few slides. So this is what biodiesel looks like here. We can have a large hydrophobic region, okay, which is non-polar. This part of the molecule is non-polar, and then we have the polar ester group. Okay, and this is made by this came from the methanol and the fatty acid to make our ester. So here we see the triglyceride. So this is what we obtain from fats and oils. Remembering fats are more saturated. Oils tend to be unsaturated. Okay, so when we extract oils and fats, we get a triglyceride, which is the 3 strands attached to the glycerol backbone. Okay, what happens is we place this into a reaction vessel, and in the presence of a strong base, okay, because the hydrolysis of the ester is base catalyzed, which is the breaking of that ester is base catalyzed, and there's usually a catalyst. So this is our base catalyst for breaking apart the triglyceride. We have 3 equivalents of methanol also in the flask. So this is allowed to react with heat, and what we will end up producing is the 3 lots of biodiesel, which is a methyl ester. We've added the methyl group onto here. So this is broken apart and create the carboxylic acid, and then we get condensation of the alcohol onto the carboxylic acid group. The other thing it will produce is it will produce 1 molar equivalent of glycerol. So we have 1 triglyceride is to 3 methanol, which produces 3 biodiesel and 1 glycerol. The structure for glycerol and your fatty acids are given in your data booklet. So let's talk about polarity, and you may recognize this diagram here. Petrodiesel is nonpolar. It's a nonpolar hydrocarbon. The only forces, therefore, that act between petrodiesel molecules are dispersion forces. Biodiesel has a polar functional group. The whole molecule isn't necessarily highly polar. It does have a large nonpolar chain, but where the ester functionality is, we can see that there is this delta minus delta plus dipole going on. So we have a polar functional group in this region. That means that where the ester functional group is, it is able to create dipole-dipole bonds between neighboring biodiesel molecules. Okay, so this changes its properties. One of the properties it changes is its hygroscopy, and you may remember this word from when we talked about sodium hydroxide. We talk about hygroscopy or deliquescence. So hygroscopy in this case is it's able to absorb moisture from the environment, and this is because it interacts with water molecules. Because of the polar nature of the ester group, it's able to attract water molecules to it. Okay, and in this case, they will form hydrogen bonds. This is because the water, okay, is a hydrogen bond donor, and the ester group is a hydrogen bond acceptor. With no water around, there will be no hydrogen bonding between the molecules. In an exam, if you're afraid of mixing this up, you could refer to it as a dipole-dipole interaction and still be okay. But the water is forming the hydrogen bonds, okay, to the ester. When it is just an ester, ester-ester, it's going to be dipole-dipole only, okay? So ester molecules cannot form hydrogen bonds with themselves. They only form hydrogen bonds with water. So because of this polar group, it means that it can absorb water molecules, so that makes it hygroscopic. We get water trapped into the fuel, and as you can imagine, this can reduce its energy density when it's burnt. Biodiesel will also have a higher viscosity. We've talked about this as being resistant to flow. So high viscosity fluids is something like honey that is thick, okay, and will thin down when we heat it, and that's because we'll lessen the effect of the intermolecular forces with heating. So it has a higher viscosity than petrodiesel because of the stronger intermolecular bonding, the dipole-dipole forces, as well as the dispersion forces. And as a number of you have noted, a lot of biodiesel molecules are actually bigger than some of the molecules that we see within petrodiesel, so they increase dispersion forces as well. And the biodiesel has a higher cloud point. Cloud point is a measure of the temperature where solid crystals start to form. So as it starts to cool down, we'll start to see solid crystals forming in it. As you can imagine, if we make biodiesel from saturated fats, then this point is actually at a higher temperature. And this can change the temperatures of which biodiesel is able to be used at. So it has a higher cloud point, where cloud point is the temperature where the solid crystals begin to form, and our biodiesel will start to lose its ability to flow. It starts to solidify. So if we compare these, we can see that the different density, viscosity, cloud point, energy content, and energy density are able to be compared between the two. In terms of density, in terms of mass per volume, petrodiesel and biodiesel are similar, but biodiesel is a little bit more dense. Okay, so it will weigh a bit more for the same volume. The viscosity of biodiesel is actually almost twice that of petrodiesel. The cloud point of biodiesel is from -3 to 12 degrees, whereas petrodiesel is -15 to 5. So this is much greater problems to people wanting to use biodiesel in equipment or cars that will be operating at temperatures under 0 degrees or sitting around in temperatures under 0 degrees in places like Canada. The energy content for biodiesel is a little bit smaller, and the energy density, so this is energy per kilogram, but the energy density per liquid of fuel is a bit lower as well. So we get less energy per litre or per gram of fuel.
So we've looked at the cloud point, we've looked at energy, we've looked at the physical properties and viscosity. So now we want to look at the environmental impact. As we've been talking about, a lot of these are going to refer to carbon neutrality, sustainability, all those things when we're comparing fossil fuels to some of our more popular or more currently used biofuel options. The carbon dioxide emission from both petrodiesel and biodiesel are about the same, okay, which is about the same as petrol. This means that the carbon released on combustion, okay, is the same roughly for both of them. The diesel vehicles produce 10 to 20% less than CO2 than petrol engines, okay? So pure diesel engines produce less CO2 and biodiesel produces much the same as petroleum. Okay, the good thing about biodiesel though is that the CO2 released during combustion is theoretically reabsorbed by the plants during photosynthesis for its production. Okay, we've talked about this. We know that that is not necessarily taking into consideration transport or manufacture, but purely for the sourcing of the oil. Okay, it's never entirely carbon neutral as there is energy expended in refining and transport that releases more CO2. Okay, so that covers our environmental impact. This question here is in your question packet. I'd like you to have a go at doing it, and we're going to go through it in class to look at it because there's a number of things that we'll talk about in regards to bonding with this question. But other than that, that's it from me for this video. I'll see you in class and we will wrap up all the information that we have done regarding fuels ready to move on and about combustion and thermochemical equations. I'll see you in class.